So we've looked at section 5.1 where we really looked at perpendicular bisectors and angle bisectors in depth. This section we are going to really look at within a triangle. So this is where we're really tying all these same ideas but into a triangle.
So this is kind of what we did in class today where we were doing the constructions of these things.
Exactly.
Okay.
So first of all, the perpendicular bisector of a triangle is a line, a ray, or a segment that is perpendicular to a side of the triangle at the midpoint of that side.
Okay.
So it's a perpendicular bisector of a side of that triangle. So if I found a point that I knew that point was dividing that segment into two congruent parts, and if I drew a line through that point, or a segment or a ray or whatever, that was perpendicular to that line, that side, then I know that I've created a perpendicular bisector of a triangle.
Which kind of makes sense because when we talked about perpendicular bisector of just a segment, this is happening, and a triangle has technically 3 segments in it, so we could do it really to all 3, right, if we wanted to.
Exactly. So I could draw in a perpendicular bisector of this segment, and I could draw in a, I don't even draw that perpendicular. It's not perfect. This is my sketch. And then I could do the same thing for our last segment as well. Say, okay, so this is maybe my midpoint, and drawing in that perpendicular segment. And guys, we're going to be exploring some cool things that happen when I look at all of those perpendicular bisectors today.
And we actually kind of explored it already today.
We did. But
now we're going to make sure we all are understanding that concept.
Yes.
So in a triangle, there are how many perpendicular bisectors? There are actually 3 of these. All right, so keep that in mind. Now, angle bisector, we've talked about, again, in section 5.1. We've actually talked about this back in chapter 1 even.
Yes.
So this is something we're a little more familiar with in a sense. But it's essentially a bisector of an angle of that triangle. Now, a triangle has how many angles?
Has 3 angles.
3 angles. So if you're bisecting an angle, essentially you're basically dividing an angle into two congruent parts.
Mm-hmm.
And in a triangle, you're going to end up doing that 3 different times because there's 3 different angles. And that's what you did today. You created a triangle. You created the angle bisectors and the perpendicular bisectors.
Right.
What's happening is there's something cool about it when you create all 3. All right?
Yes.
So,
all right. Now, we have some more vocabulary before we get started because there are some really cool things today.
Yep.
We can't wait to show you. But we want to make sure we're good with all the vocabulary. So, concurrent lines. There are going to be 3 or more, and we say or more, typically we're going to be looking at 3, but 3 or more lines or rays or segments that intersect in the same point. So to be concurrent, it's not just a number of lines, they all have to intersect at the same point.
okay. Because two lines could always intersect at one point.
Exactly.
But if you add in another line, it's not always going to intersect at the same point.
Right.
But when they do, that's that concurrent idea.
Exactly.
Okay.
And the point of concurrency kind of sounds like what it probably should be. It's that point where all of those lines are concurrent with one another, point of intersection of the concurrent lines. So it's where they're all intersecting. Now, when we're looking at triangles, I want you to realize that a point of concurrency could be inside, outside, or on that triangle.
And I'm thinking already, because of what we explored today, that the reason why we're talking about concurrent is because some of these things that we're drawing in the triangles could be considered concurrent.
Right.
And I even that first slide that you showed, when you were just doing a little sketch, I noticed that those all meet at the same point.
They do. And so there's our point of concurrency.
Okay.
Okay.
So good to know. Good to know. Now, so this all leads into, we have a couple big ideas, all right, involving one with the perpendicular bisector, the other with angle bisectors. Now, the first one is this idea, and Ms. Hargrave did an awesome sketch of this just now. You guys actually created this today in class. But when you create perpendicular bisectors of a triangle, they are going to be concurrent, all right? And that point of concurrency is called a circumcenter. You need to get familiar with these vocabulary terms, okay? This is one chapter where some vocabulary is easy to, like, when you read it, you're like, okay, I remember it, but sometimes these are ones that are not always so obvious.
Right.
So we're going to try to give you some pointers, but it may not be the solution to every single one of you. So this is, some of you might have to actually memorize.
Some flashcards may not be an awful idea to try to remember. Okay, when I'm talking about perpendicular bisectors, that point of concurrency is called the circumcenter.
So we have 3 different sketches of this. And it's based on something you guys explored even today, that when you have, this is just by looking at it, looks like an acute triangle, right?
Right.
And we drew one of these. So this is an acute triangle. Notice that when you create your perpendicular bisectors, and these are, I don't have them labeled, but I'm just telling you they all meet at a point. So that's why they're called concurrent. So that's the point of concurrency. This is what we call the circumcenter. Now, notice where that circumcenter is located in an acute triangle.
It's inside.
It's inside
the triangle.
Now, with a right triangle, where you have your perpendicular bisectors meet, it's actually
on
the triangle. And if you wanted to be even more specific, think about where that point is located on that triangle. Where do you see it?
It's on the hypotenuse.
It's on the hypotenuse, and even better, where on that hypotenuse?
The midpoint.
Yeah.
Because we know that it's a perpendicular bisector of that segment, so I know that those
So these would be, we know, because if I tell you these are perpendicular bisectors, that those are congruent pieces.
Right.
Now, you don't necessarily need to know it's at the hypotenuse's midpoint, but, you know, it might come in handy sometimes, okay? Knowing where that it's on is a little bit more helpful. All right, the last one, this is one that's a little harder to explore, mainly because in an obtuse triangle,
they all meet outside the triangle. And we would really need to have extra paper beyond our triangle to really look to find where they all intersect.
Exactly. Now, one thing that I think both Mrs. Hograby and I kind of agree on is that with this idea of a circumcenter, there is a reason why it comes about. When you create, and I'm going to kind of click this in here. Notice that if I surround that triangle with a circle.
Okay.
What do you notice? What are you thinking anyway?
Well, I noticed that first of all of the vertices of the triangle are on that circle. So that's what you mean by surrounding it. And it looks like that circumcenter is the center of that circle.
It actually is.
That's pretty cool.
Yeah. And this is going to kind of support what this next theorem is going to be in just a minute. All right. You're going to see something kind of cool that happens here. All right. So I don't want to give it away. And I'm going to just show you on the next pictures kind of why that's the case. So again, with a circumcenter being the center of the circle that surrounds that triangle, this is what we call a circumscribed triangle, which means it's surrounded by our circle. All right, all the vertices are on the circle as well as it's surrounded by it. Okay. The center of the circle actually ends up being the circumcenter.
That is pretty darn cool.
Of that triangle.
I know in years past when I've said this in class, my kids went, Mrs. Hograby, you just blew my mind.
Holy cow. Now, the reason why this is also useful is if you think about what we've talked about, just perpendicular bisector from just a segment, okay? So this is a perpendicular bisector of, well, didn't do a very good job of tracing that. So a perpendicular bisector of this segment here.
Right.
Okay. We explored, not by definition, by the theorem, is that any point on the perpendicular bisector was equidistant to the endpoints of that particular segment, right?
Right.
So the distance from this point to each of these endpoints are equidistant. This is another reason why, if you think about it, the distances all the way through here are going to be the same.
They're all radius.
They're all the radius of that circle as well.
This is pretty cool
Okay,
stuff.
so they're all that connection there. So this theorem that I'm about to show you is not necessarily a brand new theorem. It's not a brand new theorem.
All right. This says it's the concurrency of perpendicular bisectors of a triangle. And it just says that the perpendicular bisectors of a triangle intersect at a point that is equidistant from the vertices of that triangle.
Okay. And the reason why I said it's not really that much different than what we've learned is because this is, to me, this kind of sounds a little bit like the perpendicular bisector theorem.
It does.
But it's not the exact same thing, exact same, because there's more stuff to it.
Right. So looking at this, again, this is saying that we've got a perpendicular bisector, right? And we've got all of these perpendicular bisectors drawn in our circle. So we have 3 of them. And we see that point of concurrency, which we've just called the
circumcenter.
Circumcenter.
Good.
So when you've got a circumcenter, here's what's really cool about it, is we know that if we drew in that circle that's surrounded, oh, and this is just going to be, okay, I'm not even going to draw it because that is just awful. Oh
but
my
remember
gosh.
from the last slide, remember
For a second. So when we've drawn in that circle, notice that those vertices we said were all on the circle. So to go from that circumcenter to any of those vertices, we would be, and it's harder to see on the right triangle, but from that circumcenter to any of these vertices, they're all radius of that circle.
And we know all radii in a circle are
We know all radii in a circle are the same. So all of these distances to those vertices are all equal. Now again, this is another one that says equidistant. So we're talking about equal distance, not congruent.
So if I was kind of applying this, I would have to first know I had some perpendicular bisectors, right? And I would know that they all meet at point P, which basically means that PA is equal to AB. P is equidistant to, or you want, what do you want
I
me to
was
say?
just going to write down that P
is the circumcenter.
You got it.
Sorry, I had mentioned that and then I got ahead. So P is the circumcenter of that triangle, which basically means that the distance from P to A is equal to P to B, and so on and so forth, and then PC.
Right. So as long as you know you've got either the circumcenter, if they use that vocabulary word, we know exactly what that tells us. Or if we could see that they were perpendicular bisectors for sure, then we could say that, yeah, all of these segments. Now notice that the relationship here, we knew we had perpendicular bisectors, which deals with segments, deals with the sides, but the relationship with this theorem is that it really goes to the vertices to form that equal distance.
Which the vertices of a triangle are points.
Right.
And when we applied this yesterday, basically, we were talking about it equidistant to the endpoints of a segment. Again, points as well.
Right.
The endpoints of the segment are the vertices of the triangle.
Right.
So this is, I mean, literally almost identical to the perpendicular bisector theorem. This is very much like that perpendicular bisector theorem. It's not the same thing because perpendicular bisector theorem only involves one segment, where this one involves technically three.
Three, and that point of concurrency.
And knowing that word is important as well. Like Mrs. Hochgraby said, sometimes we might say, here's a circumcenter. You have to know, okay, what does that mean? That means it's equidistant to the vertices. All right? So keeping that in mind. Vertices are points, not angles.
Right.
All right? Now, the other point of concurrency that we're talking about is what we call the end center, okay, of a triangle. The end center is also a point of concurrency, but it's the point of concurrency of angle bisectors.
Okay.
So it's kind of, again, another vocabulary term we need to know. But some cool things about it we'll show you in just a minute. So when you create angle bisectors, we saw this today, all three of them in a triangle, they're all going to meet at a point we call the end center. Now, this is an acute triangle, okay? This is our right triangle, and we have an obtuse triangle. We explored these today.
Now, what's cool about these all meet inside the triangle. There's nothing here that's on the triangle, nothing here that's outside.
All of them.
When we're thinking in center, it's always inside that triangle.
And another cool thing about it, kind of what we were doing earlier with the circle idea, I'm going to show you all the circles that are formed. But notice this time, the circle is actually not a circle. This is inside the triangle, which means that it's an inscribed circle.
Okay, so circumscribed means it's outside the circle touching its vertices. Inscribed means that it's inside. The circle is inside that triangle, but it's touching the sides.
Yeah, notice how the circle is touching the sides of the triangle in all of these. And just again, notice the end center ends up being the center of your circle as well.
These are some pretty cool relationships. I have to say, I'm pretty impressed with triangles. Who knew all of this stuff existed within a triangle?
And a connection to circles as well, right? But again, the key about end center, it's the point of concurrency of angle bisectors, and it's always going to be inside your triangle every single time.
Yeah, and guys, the whole idea too with these vocabulary terms, in center, think you have an inscribed. A circle that's inscribed within your triangle.
Exactly.
Where circumcenter, it's the circle's circumscribed around that triangle. Okay, so here is the theorem. This is the theorem of the concurrency of angle bisectors of a triangle. And by the way, do you guys notice these are not like convenient names to be using in a proof? We're not really going to be using these in proof so much as just being able to apply the concepts.
Yes.
So don't stress about the names as much as what they're saying.
Yeah.
That's
and
really
guys, one thing you've noticed is when we use a theorem a lot in proof, we have a convenient name for it.
Yes.
We try to do that because we honestly don't want to have to write this lengthy name either. Okay?
Right.
We get it.
So this says that the angle bisectors of a triangle intersect at a point that is equidistant. And we know this point again is called our
in-center.
In-center. So I'm going to even write this. If we have the in-center, then we know that at that point, that in-center is equidistant from the sides of the triangle. Now, I'm going to go back, and I think this one I might be able to handle. We're going to see. If I drew that circle in again, okay, no, not so much. We're just going to go back because we have some beautiful pictures. Why try to mess with it? All right. So notice that this circle being inscribed, we've got that's touching the sides, right? It's touching the sides. Now, it doesn't necessarily touch exactly where my line is going through, my angle bisector, but it's touching the sides of my triangle. And what's really cool is if we drew in here, let's try to make this line skinny enough to where you can follow it. But if we drew in from the center to those points, I want you to notice, what do you think is true about from the center to these points?
Well, I know that those are radii.
They're radii.
Okay? Because distance from a center of a circle to a point on the circle is radii. And I know that those are congruent, are equal because radii are all equal. But I'm also thinking of the fact that when you're drawing that distance, it's also intersecting that triangle. And when I'm talking about the distance from a point to a segment, it's the perpendicular distances. And I can even tell by even your sketch, those resemble perpendicular segments as well.
So we're going to be talking about some angle bisectors forming those perpendicular distances, which sounds a little bit to me like we're talking about something from the angle bisector theorem.
Yep.
And this is basically what it's saying, is that that point that's in center is equidistant from those sides. So from that center of our circle to each of those perpendicular distances to the sides, those would all be radii. They're all equal distance. So as long as I know that P is the end center of our triangle, then we know what?
Then we know that PF is equal to PD and is equal to PE. And those are all those perpendicular distances.
Yes.
Right? I want to stress again what Ms. Huckerby said. I think this was huge. Notice those distances are not actually on the angle bisectors.
Right.
Sometimes it will. It has to be a pretty special triangle for that to happen. Most of the time it's not. So you don't want to just measure the length of that perpendicular bisector to the side because those are not actually perpendicular distances.
Right.
So let's apply these now. We have a couple examples. Notice the given gives you some, or the given information here. I'm going to label some stuff in this picture so that way we can kind of work with it. So the length of OS is 10. The length of QR, this length right here, is 12. We know that PQ is, this whole thing is 22.
Okay.
Now, before we actually go ahead and find all this stuff, one thing that I would encourage you to consider is what exactly is happening in this picture.
Yeah, that's what I was thinking.
What is it that we see?
I noticed that I see some segments coming off angles and I see some segments coming off of sides. So I really want to decide, okay, are these angle bisectors or are they perpendicular bisectors?
And that's really all we're worrying about right now. We either have angle bisectors or perpendicular bisectors. We will have two more things we'll see in this chapter, but these are the big question.
Okay. And I noticed that the pieces that are marked congruent don't deal with the angles at all. So I don't know that it's angle bisectors.
I like that.
But I do notice that I do, on each side, I am showing that those points that are on the yellow lines are perpendicular and they are bisecting those segments. So these
some congruent and some right angles, right?
Yeah, so these are definitely perpendicular bisectors.
I like your observation. There wasn't any congruent angles labeled. They didn't say anything about an incenter. They're communicating perpendicular bisectors. So we know what we know about perpendicular bisectors of a triangle.
Okay.
What do we know about them? Perpendicular bisectors.
We know that they meet at a point called our circumcenter.
Okay.
And we learned through our theorem that that circumcenter is equidistant to all of the vertices.
Okay. So I'm just going to make a little side note of that. Okay. So let's feed off of that. Let's see if we can use that idea. Let's start with segment OP.
Okay. So OP, I'm looking at it. Well, I already know that OS was 10, so I know that because it's congruent to SP, SP is also 10, so therefore I know the whole thing is 20. Good. Well, that was pretty easy. I didn't even need any theorems or anything to do that one.
That was more using the perpendicular bisector idea.
Yeah.
Okay.
And that it was marked congruent.
You didn't even have to know that. True. All right, let's move on. RP.
RP. So looking at RP, okay, I noticed that that is one of the segments that goes from that circumcenter to a vertice. And I know that they should be the same distance from the circumcenter to all vertices. So since they gave me that QR was 12, I know that PR also has to be 12.
Good. I like that. You kind of looked at that. And I went ahead and label what she said. All of these distances from the circumcenter to each vertex are all the same.
Right.
All right, moving on.
Okay.
OR.
OR. Oh, okay. Let's see. OR is another one of those from the circumcenter to the vertex. That's also 12.
Okay.
And TP. Okay, that I don't know enough information just by looking at what I've got there. Let me see. I know that TP. Oh, wait. TP is marked with a. I was looking at the wrong segment. Sorry. TP is marked with a congruence. So I know that those QT and TP are both going to be the same measure, and together they're 22, so that's 11.
Perfect.
That's funny. I was looking at the wrong segment. Okay. Next one. Let's see. We've got which segments are congruent. Now, I like the way that you started the last one.
Yes.
As we look at this problem, as we look at this picture, what pieces do we even have on this picture that are marked?
All right. Well, I see, like you were saying, I see segments going to the sides that are perpendicular. So I might be dealing with perpendicular bisectors, but the only problem with that is I don't see any bisecting of sides. I don't see congruent segments.
And when I look at VZ and VX, they really don't look like they are either. Okay.
But I also see segments coming from the angles, and the good thing about that is that those are actually labeled congruent angles. So these are angle bisectors, which essentially means that angle bisectors all meet at a point, and we call that the incenter. And the incenter is equidistant to the sides. And when you're talking about equidistant to the sides, it's got to be that perpendicular distance.
Great. So even when we're dealing with angle bisectors, you're still going to see things possibly marked perpendicular, but they're not perpendicular bisectors. But we know that it's the perpendicular distance to that side.
Good.
So that's what we're looking at. Okay, so which segments here are congruent?
Okay, well, we're talking about segments. So if I know that the incenter is P, and P is equidistant to the side, so I know the distances from P to V and P to U and P to T are all equal. Perfect. That means that they are congruent. So I could essentially say PV is congruent to segment PU, stinky, is congruent to segment PT.
Great. All right, now it says find PT and PV. Now, what do you know about PT and PV?
Well, they're the same measure. Wait. Yeah, they are the same measure. And they also are the same measure as PU, the stinky one.
The stinky one, yes.
Which I look at the picture, I don't know any of them.
We don't know any of them.
Okay.
But we do have some other pieces of information that we do know in that picture that may help us.
Probably so. And then if they give you something in the picture, more than likely you're going to use it. So I'm going to look at that picture, and I see the stuff they gave you is TY and segment PY. And I'm thinking, well, those two segments that are labeled, how do they relate to PT and PV? Well, PT and those two segments given actually form a right triangle.
A right triangle.
And we talked about this not that long ago, that if I know two of the sides of a right triangle, and the right triangle I'm talking about is PTY, then I can use Pythagorean theorem to find that PT.
Absolutely.
Okay.
Now, if I think about in terms of A, B, and C,
the hypotenuse is the one we got to be most careful with,
Right.
which is the 13. So that's the C.
right. So as long as I know that, then really these
It doesn't
two
matter.
sides won't
So
matter.
I'm going to set it up. I'll just say 12 squared plus, I'm going to say B squared or PT squared, however you want to say it, equals 13 squared. So I get 144 plus B squared equals 169. I'm going to subtract 144 on both sides. So B squared equals 25. Take the square root, and I get B equals 5. Now,
Technically plus or minus 5, but we know we're not going to deal with the negative
Yes.
side length, okay?
so B is actually 5, which is PT. So I can say PT is equal to 5 and PV is equal to 5 because they're the same measure.
And you could even say that PT was equal to PV, which both equal 5. So however you want to write that is fine.